Hello everybody, this is Nino Ivanov, and in this video I shall go about telling you how to implement logical triangulation in practice. This has been a question in recent times asked to me by Carolina, but in the past it has also been mentioned by Mikola that an implementation of this theory in the language C would be faster than my Lisp implementations. And Patrick, who is actually a master of the NARS implementation, was also curious in what ways logical triangulation can be shown to work in practice. So I actually did an implementation in C, but in order to understand what's going on there, I'm going to lead you through a short presentation and a short recap of one or the other thing. But I am assuming in all of this that you are in general acquainted with logical triangulation, and I'm not going to go much into that. If you're interested in that, look at my previous videos. Alright, what is the general principle of intelligence overall? Well, I say a system is going to get challenges from the outer world, generally speaking a user, and the system shall reply to the user. So in reality, you could make a simplified assumption by saying that communication truly is the exchange of symbols between these two entities. And a system will be intelligent if the exchange of symbols is not random, if the exchange is proper. In this way, proper is meant to signify a usual exchange. So if you say hello, you will expect to hear hello. You will not expect to hear pancake. It is a symbol, but it's nonsensical to get it as a return. So, what does it mean to get something usual? Well, you can say that certain things, certain symbols which are perceived, are grouped in some usual way. Like, for instance, if your hand is lying on the table and you lift it, you are expecting that your fingers will be lifted together with the rest of your hand. Well, if you're seeing things in this way, you can say that it is all about grouping. And this really is the core of logical triangulation, to make out which sort of grouping is appropriate. So, for instance, if you are having a sequence of symbols A, B, C, A, B, C, A, B, C, what would be a proper way of grouping them? Well, I'm showing here one example. I'm saying you are seeing B, C 3 times, and you can group this, and this grouping of those symbols you can call X. X is just this, the notation that B is next to C. Alright? And actually you can give this group an own name. You can call it X. So instead of looking at A, B, C, once you have grouped B and C into X, you can now be looking at A and X. So really you will be having now AX, AX, and AX. This once more you can group into Y. And then you will be having Y, Y, and Y. Again, you can group the last 2 Y's into Z. And then you can group Y and Z into Q. And once you have done that, all the perception will have been grouped. And you can see already that there is some sort of hierarchy in the grouping. Some things are grouped at the expense of other things. If you group B and C, it means you are not grouping A and B, nor C and A. You are specifically grouping B and C. And my presumption goes that intelligence truly dictates what to group and what to make to follow after what else. Basically, what comes after what and what belongs together. It is the basis of logical triangulation that such groups are done each time of two symbols, and no more, no less. Such symbols, which are the fruit of perception, A, B, and C, I call elementary, and such like X, Y, Z, or Q, I am calling superatoms. Like these symbols, like A, B, C, are elementary atoms, and X, Y, Z, and Q are superatoms because they are not immediately perceived, but are arising out of grouping. So, besides structure, grouping also indicates how to continue the perception of a given symbol. If you get B, well, obviously you are continuing that with C. That's every time what you see after B. You don't see B and then A. You see B and then C. So that's exactly what you're going to say. If you have A, the continuation is even more interesting because you have the option of continuing A with X. You have this 3 times. So A is continued by X. An elementary atom can be continued by a superatom. That's just fine. And even more interesting it becomes when you're looking at Y, because Y obviously can be continued with another Y. However, Y can also be continued with Z. Which one is the winning one, so to say? Like if I give you Y, which one will you pick? Well, that depends which bond will turn out stronger. The bond of Y followed by Y, or the bond of Y followed by Z. That is exactly the sort of structuring that logical triangulation shall help you to decide upon. And now come the 4 possible logical triangles which you should be acquainted with already. Basically, logical triangulation is about connections which evaluate each other. If you're having 3 atoms or symbols, K, L, and M, then these symbols can have in each case 2 possible relations. They can be neighboring each other, like here, or they can be replacing each other, like here. And this gives us 4 possible correlations of K, L, and M, and of these, in turn, 2 are consistent, and 2 of them are nonsense. I mean, if you like, I can just very quickly go through that. If you say that K is coffee, right, and L is sugar, and M is tea, then coffee is drunk with sugar, coffee is like tea, and tea is drunk with sugar. But it is obviously nonsense to say that coffee is drunk with sugar, coffee is drunk with tea, and tea is drunk with sugar. Basically, one of these 3 relations is wrong, or perhaps all 3 of them, but you don't know which one exactly. You are finding that out by letting one side correlate with many other sides, and then you find out whether its connection is finally becoming stronger or weaker. Moreover, same story here, you can say that coffee is like tea, tea is like cacao, and obviously cacao is like coffee. But if you're saying that coffee is like tea, tea is like cacao, and for that reason you have to drink coffee with cacao, this is nonsense. So these are the three logical triangles, and they give you two results, basically. Either a connection should be more neighboring, a thing should happen together with another thing, or two things are alternative, and they should not be observed together. If you go back, it would therefore mean that B and C are strongly connected with a VIC connection, that is, this sort, vicinity connection, yeah? And A and B aren't, because they are separated here. B preferred the bond with C before the bond with A. So, once you have established such structures, you can go about answering requests of the user. So, if the user is saying A, we saw before that it should be replied to with X. However, X is an abstract atom. X is a superatom. It is not a thing of perception itself. For that reason, X must be decomposed into those elementary atoms which finally make up X, in this case BC. So if the user says A, the machine will reply with BC. And now comes basically the new stuff. What you heard so far you should know by now, already from previous videos. But this nice theory of having two atoms and a superatom is now being shown how to have it implemented actually as arrays in C. Well, I'm going about it this way. Every atom is having 4 dimensions. The first one, for instance this number 100 that you're seeing, is the superatom, that is X. X is 100. 100 is consisting out of a left subatom, that is B, alright, 2 is B, a right subatom, that is here 3, C is 3, and an atom value, here minus 1000. This atom value really denotes the type of connection between B and C. If the value is negative, this is a vicinity connection, so to say coffee with sugar. If the type is positive, that is an analogy connection, that is tea or coffee. So, you realize these two depictions are different only in the atom type. This one is negative and vicinitary, and this one denotes an analogy being positive. Here you see one further example. A with X, it's the same X as here, makes up for the abstract atom Y. So Y is 101. A is 1, and the atom 100 is the atom number of X, which we saw here. So it goes here, and because it is a vicinity connection, the value is minus 800. So this is going to be the basic structure we will be working with in this implementation. Number, left subatom, right subatom, and value. Negative values denoting vicinity, positive denoting analogy. Thereby, the more negative a value is, the stronger the vicinity connection is, the more positive the value is, the stronger the analogy connection is. That is a rather strong vicinity connection, and that is a kind of maybe analogy connection. Not too sure whether these two things are analogous, you know. Alright, let's go to the next one. So, now that we know that, what do we do about it? Right? How do we use this knowledge in order to structure the input? Well, let's say that the input is really A, B, C, A, B, C, and A, B, C. this can be parsed as numbers, each symbol being denoted by one number, into 1, 2, 3, 1, 2, 3, 1, 2, 3. I shall not discuss exactly how the parsing is happening, but yes, obviously there is a parser, and all you need to know is that it turns symbols into single numbers. So, you know that you should group B and C because this is having a really strong vicinity connection. You are selecting the strongest vicinity connection and you are grouping it. What you are essentially doing is that you are replacing each occurrence of 2 and 3, 2 and 3, and 2 and 3. You are replacing these occurrences with the atom number of X, that is with 100, because 100 is denoting 2 and 3. So from okay, this should have been 1, 2, 3, 1, 2, 3, 1, 2, 3. You are going to get 1, 100, 1, 100, 1, 100. This is after several replacements. You start with one replacement, then you go for another, let's say the second 100 would have been replaced, and then finally the third 2, 3 is replaced with one further 100. You do this recursively. That is, in the next step, you will be replacing 1 and 100 by 101, which was the atom Y, because the atom Y consisted of A and X. So, you will continue that until in the end, the entire input will have been reduced to just one number, which is the entire structure which is made out by that input. So, now that we are doing the grouping, what do you do after you have grouped two atoms? What do you do further? How do you do triangulation? I'm saying every time after you have decided to group two atoms together, you pick that side and use it in order to perform logical triangulation. So we picked B and C and said that this is X. Alright, then let's take B and C and try to do with that logical triangulation. B and C is having the left atom of 2, that is B, and the right atom of 3, that is C. So, how do we go about constructing a triangle? Well, we search for some other atom, C and D, for instance. And C and D has one relation in common with the original one, that is the 3. They have the C's in common here, right? And basically, that is the second side of the triangle. If you have found such a second side of the triangle, there's an interesting effect. The third side is absolutely clear by then, because obviously the third side must be the other two atoms that are not in common. If C is in common, then obviously the third side consists out of B and D. So if you have a second side, you automatically get the third side. The only question that might arise is whether the third side is already known, like for instance here with the atom 300 and some value it has had before, or whether the third side is really the result of hypothesis. So it is either known or it is concluded, but once you have two sides, really you have three. I am calling the second side which you find the conjugate, and the third side I'm calling the cohabitant. Yeah, basically that's about it. That's how you do triangulation. When you have found such a second side, you are already set to go. That is actually, if you allow me this little digression, the special thing, and what differentiates a conjugate from a cohabitant. A conjugate must be known. A cohabitant can be concluded. It can be known, and it can be concluded. The conjugate must be known. You must start somewhere to construct your triangle. It's easy, actually. Now, obviously, you're going to ask me a question. What makes it clear which one is the conjugate and which one is the cohabitant? After all, if you're having the triangle of B, C, and D, you could be starting with BC. BC is given, yeah? But you could be starting with B and D and concluding CD, or you could be starting with CD and concluding BD. Well, truth be told, you will find by that method both triangles. It is in truth the same triangle, just once you start with finding one side and then you start with finding the other side. You should account for that effect. That's nothing bad. You just have to decide what you're going to do about it. Are you going to eliminate the second triangle? Or are you going to, for instance, work with all triangles, however, give them only one half the effect, because you know that in fact you will get every triangle twice. Keep that in mind when you are doing your own implementation. So what does it mean to actually triangulate? Like, that sounds really cool, but what does it do? It means that you are adjusting the value of structures, okay? It means that you are saying, for instance, here before, whether B and C are really a good idea or not. So we're going to look here at two triangles, E, F, and G, and they are different only by one thing. In the one case, F and G are a ANA atom with the value of plus 500, and in the other case, they are a VIC vicinity atom with a value of minus 500. And the adjustment is happening, at least in my implementation, according to the following formula. You take the value of one side, that is of E and F, that has the value of minus 100. This is really the same atom value that we were discussing before here, okay? So you're picking this value, and you're now adjusting it. It is itself plus. You then multiply the absolute values of the other two sides, okay? Basically this. You take the square root out of it, so that this thing doesn't skyrocket in absolute value. Okay, so you take the square root of this multiplication. This is giving you 1 million, and the square root of it is 1000. And you are multiplying their signs. So that gives us minus 100 plus minus 1 from the 2000 plus 1 here, like minus 1 times plus 1 from the plus 500 times essentially 1000. And that is going to make the original minus 100 a much stronger vicinity connection. It is minus 1100. You are saying, hey, if this is vicinity and this is analogy, then this is really, really, really clearly vicinity. Okay? You do this obviously for all of the three sides. I'm just showing you one of them, but it really applies for all of them. This is also going to get stronger, because you're going to say, hey, wait a moment, if this is so and this is so, then this is obviously going to be increased. So a positive triangle is keeping the signs of all involved sides and increasing the absolute value. That means that these atoms have become more reliable. Now let's look at what happens with the negative triangle. The computation is really the exactly same thing, with one change. The minus 500 make it here times minus 1 instead of times plus 1. So you're going to sum minus 100 not with minus 1000, but with plus 1000. Essentially, that flips the connection. You're going to get plus 900. From the weak vicinity atom is going to arise a rather strong analogy atom. Basically, these two sides, being much stronger than this side, are practically eating it for breakfast, and they are forcing it to change its type so that the triangle becomes again positive. In the process, each of the other two sides will be also badly affected by the negative triangulation. Their absolute value will become weaker too. So this is basically the price you pay for having incongruent connections. They are unreliable, and you will not want to keep them as so strong as they were before. You will say they were somewhat less reliable. And this is going to continue until you manage, as here, to flip one connection so that the triangle becomes positive. If I would draw this again now, it would be vicinity, vicinity, but here now analogy. Okay, you're obviously not going to do just one triangle. If you're going to have here BC, you know, this is this thing which we decide to group here, right? This BC. Then you are going to find a lot of possibilities potentially where to let BC participate. Some of these possibilities might be positive, others might be negative. Some might be actually new conclusions. For instance, you didn't know B and D, but you did know B and C and D. This is basically the main mechanism of reasoning of my logical triangulation system and the reason for the name, quite obviously. Now let us have a look at the atom numbers themselves. I'm mentioning this because I can imagine that you will be curious and eventually you will want to look at its knowledge base. Alright, so from the possible numbers, you're going to have in the knowledge base an array of arrays. That is a two-dimensional matrix, okay? Each atom consists out of 4 elements: its atom number, its left subatom, its right subatom, and its value. Let's look at these atom numbers themselves. Well, 0 is a special atom. You don't use it in anything. Basically, if an atom has the atom number 0, that means something is messy with it, and you can't handle it normally. So you're never going to really see a 0 atom number if everything is fine. You're going to see 0 if I'm doing something special somewhere. For instance, finding out that an atom has no conjugates and no cohabitants. It cannot do triangulation because nothing else is known. Then all the conjugates and cohabitants will have the atom number 0. Okay? Atoms can only be positive. They can't be negative. Now, being positive, what are the elementary atoms? You remember here in the very beginning, I told you that when you're grouping here A, B, C, finally into X, Y, Z, and Q, that A, B, C are elementary because they come immediately from sensors. They are not the result of some intellectual process. They are simply kind of seen that way. Well, these elementary atoms have a range from 1 till X. You determine what X is. But this gives you the absolute count of elementary symbols that your system can work with. In the implementation I am going to show you, I picked 10,000. That means the system can essentially know 10,000 different symbols. If it runs out of symbols, my parser is starting to do funny things. But essentially, you're saying that 10,000 is the limit. Okay? Everything under it is an elementary atom. And the rest, that is from 10,001 up until the maximum value of knowledge, are your superatoms. They are these atoms which have this structure. You won't see the elementary atoms in the knowledge array because it's pointless. They are elsewhere. There is a parser array. They are somewhere, but they are not in the main knowledge array. Okay, because they are not having any subatoms. It's pointless to show them that way. Superatoms are shown that way, and you'll have here a number above 10,000 in my implementation, and then 2 numbers here which may be above or below 10,000, but definitely above 0 and a value. If you happen to see 2 0 atoms here, that is because I'm trying to prevent triangulation. This is happening when I am populating the knowledge. Okay, so when the system in the beginning is empty and doesn't know anything, then you will see here zeros. So this is basically the values of the atoms. The atom values, the atom numbers, pardon me, the atom numbers are recycled. There's just one constant size of the knowledge array, and when a new atom is learned, for instance this, with the left atom 11, the right atom 22, and the analogy value 33, then the oldest atom is being deleted, and its atom number is being reused in order to signify the new atom. You are recycling atom numbers. This is going to have a funny effect, by the way, in the beginning, but I'll come to this later. So, just remember, the count of atoms is constant, but what an atom means really depends on whether that atom hasn't been actually forgotten. Because when it gets forgotten, it gets recycled. So, how do you get to know atoms? Like, it's nice that we can work with them, but how do they ever become part of the system? There are really only two possibilities for that. The first possibility is if you have still input atoms to hierarchize, that is, still input symbols to group together. But it just so happens that you don't know, for instance, here BC. Alright, you have KLABC as the end of your input window, but you have no idea how to group it or fold it into a superatom. Then you are generating a hypothesis. You are saying, okay, I will simply now say that X means BC and that it shall have some sort of initial vicinity value. That is how you're going to create an atom. It may turn out that that was a wrong assumption in the further reasoning. So this is just a hypothesis, and it can be overturned later on. The other possibility to reach a new atom in the system is by conclusion. If you didn't know that B is leading to D, then you can conclude that. If coffee is drunk with sugar, no, if sugar is drunk with coffee and coffee is like tea, then sugar is being drunk with tea as well, okay? And if sugar is drunk with tea and sugar is drunk with coffee, then coffee and tea are similar. You can basically have these two conclusions here. Doesn't really matter, but point is, once you have two sides of a triangle, the third one becomes automatically part of the system once they are involved in triangulation. So conclusions are your second possibility to get atoms into the system. So, all right, you grouped everything. Fine. Now what? You reached some sort of top hierarchy. Well, I am making you a little proposal. While you can continue with the evaluation and so on, which I will show in a moment, it's not a bad thing to actually do a reconsideration. Because remember, each time we grouped anything together, we performed with that new side, with that new group, with that new atom, we performed triangulation. So in fact, it can turn out that some group, which in the beginning looked like a very, very good idea, is later shown to be nonsense. I mean, just remember here, here E and F looked like a good idea. But after triangulation, E and F no longer look like a good idea. They look like analogous, not being grouped together. So, what you can do is to simply keep the knowledge gained from triangulation, but dump the entire hierarchy and simply start again and say, okay, so I have A, B, C, A, D. what do I group together? And I'm giving you here an example. C and A continue to be a good idea. All right, so they are grouped into F in both cases. However, the atom B is no longer attaching itself to A. After triangulation, for instance, it might rather decide to attach itself to F and form the new atom I and change the entire hierarchy. For that reason, reconsideration is something which is going to make your system smarter and more consistent. Now assume that you really managed to do all the hierarchization, you really got the structure of the entire input. Okay, fine, you did that. Now what? You'll have to somehow reply. So let's say that the human told the machine A, B, C, A. Then what are you going to tell to that? You have found out that you can group that finally into the atom G. Now, you're going to search knowledge of the system, already existing knowledge of the system, for an atom S. S should ideally be a strong vicinity atom, and G should be its left subatom. So, if you remember the atom structure before, S would be the atom number, G would be the left subatom, and then S would have a right subatom. I'm giving it here the name R. R would be the reply of the machine. The point is, if R is actually a superatom, you can't just spit out R at the user. You will need to decompose R until you reach elementary atoms. So, in this case, NOP. And the effect of saying A, B, C, A, after structuring it, triangulation and everything happening here, you are then seeking S, finding R as the right subatom of S, decomposing R until you reach elementary atoms, and replying with the elementary atoms. That's really all there is to it. That's how you reply to people. Okay, that was the ideal situation, but it does not always happen that way. Unfortunately, you do not always find an atom S. In particular, if your input is complex, it is not always easy to know already how to answer to some certain sentence. In that case, I am having the following algorithm. I'm saying, alright, the top structure of the hierarchy, in this case G, is leading nowhere. It needs an atom S, but S is not found. So we decompose G into E and F. We take F, if we forget about E entirely, and now we do as if F is the top of the input hierarchy. Why? Because G essentially is your present. Okay, this is just what just happened right now. If you have no control over the entire situation, okay, then perhaps you have at least control over what happened most recently, the last thing what happened. Okay, like you drove a motorcycle, you crashed, you fell down. Now it would be good, let's say that is G, and if you were smart you would know that you need to get up and call the ambulance. Unfortunately, you're not smart enough and just you hit your head a bit, you can't find the reply to the entire complex situation G. So you're seeking the most recent thing, you fell down. You try to find a reply to that, for instance, get up from after having fallen down, right? So you're then looking not for S, but for T, where T is a top atom, like a superatom, so to say, and it has a left subatom F, a right subatom W, and you're taking W. You know, just like here, you are having S, like you're having G as the present, S as the knowledge, so to say, the superatom, which relates to the present, right? And the superatom is having a present and the continuation of the present. Here, T is the same story. It is having the present and the continuation of the present. And if you find such a W, then you might be able to reply with the subatoms, like until you reach elementary atoms, in this case NaNa. So if the human says A, B, C, A, and there's no reply to that known, then the machine reply will be Nana. An interesting thing to note here. The reply would have been Nana even if the present would have been CA, without the AB part. Why? Well, because G wasn't known. There was no superatom S, which could give us some fancy other reply. We just knew how to reply to C and A. Okay, what would happen if T would not have been found? I would have done the same thing recursively again. I would have split this right leg F into C and A. I would have taken A, and I would have most likely discovered the atom E with A and B, and I would have given the reply B as the machine's reply. Okay, what would happen if this atom has no known neighbor? If it would be some sort of, I don't know, some sort of atom Q or whatever, and Q has no known neighbor. Well, then the reply is none. The system simply doesn't tell you anything. If it doesn't know what to say, then you're going to get zero response. Now, that was an interesting show, but once you hear some sort of information, it usually relates to something else too. If you hear hello, you will react, for instance, differently when it comes from a friend or when it comes from a boss. You will be more polite and more formal with your boss, whereas more cordial with your friend. And that really is a matter of context. We can actually simulate context, at least to some degree. We can say that the system shall have some sort of working memory, for instance, 10 atoms, okay? And it is simply remembering the last 10 elementary atoms. So, if you're having here this exchange between human, machine, and human, then the machine's working memory is containing the entire last response of the human, the CCAMN. It is also containing the last machine response of BCC. It is containing the last human response of A, and it is containing the last part of its own response of Nana. Okay, it's containing the A. Whatever happened before the NaN and the ABCA is being forgotten. It's, so to say, too old. But this sliding window is going to make the system a little smarter, a little more aware of a general situation what it is in. It is not just going to reflexively reply to the last thing the human said, but it's going to take a bit more context into consideration. You're not forced to do that in your implementation. It just makes things a little smarter, working better. Call it as you will. Okay, what else can we do to make the system smarter? You can let it have daydreams. That is perhaps a bit of a brave expression if one looks at a machine, but really there's no other way of calling that. So, what happens when a machine replies? Well, the human tells something upon it. If the human tells A and the machine tells B, then the human will tell C, and so forth. This is a hypothetical conversation. It doesn't happen really. The machine does not know for sure what you will say. It can only estimate it from past knowledge. But what would happen if it does estimate it? Well, it would develop the interaction, right? And it could do triangulation based on this hypothetical conversation. It could evaluate how likely things are going to continue in the future. What is going to happen after it gives you a reply. And it can do that actually several times. I'm calling these cycles daydreams. You can decide what depth they shall have, so to say. And you're letting the machine evaluate basically these potential future conversations and do triangulation based on them. And in the end, it might give you a different reply than would be its original and naive reply without daydreams. Okay? If the machine would have to answer you immediately, it would tell you B. But after daydreaming, so to say, potentially extending the conversation twice here, and doing triangulation, it is going to give you another reply, P. Each time a daydream ends, it is returning to the original present. Like, what's happening now, actually, okay? What was really the input where the daydream started? And when the next daydream continues, it is again going to do a hypothetical conversation and, yeah, again triangulate and evaluate its connections and structuring. So now I told you everything what the machine can do. It gets input, it tries to structure it according to the most strongly weak connected atoms. Every time it pairs some two atoms of input, it goes ahead to do triangulation. Every time it does triangulation, it may do it several times with reconsiderations. And even that may be extended by daydreams, that is, by hypothetical ideas of how the conversation could continue in the future. Having done that, it will try to find a structure which is the continuation of the present into the future. And this structure will be the machine reply. Everything clear so far? Well, I hope so. Because now comes the interesting part. Now I will show you the implementation. Now this, don't worry, this is an image still. This is not a real thing, but it is showing you where we will be going now. We're going now to look at the actual implementation. First, we will need to generate the knowledge base. It will be empty. It will be just full of placeholders for future knowledge. And it will be done with the command atomgen, like generate atoms. This is going to create the file atom data. And when you're looking at atom data, it is going to begin at 10,001. Do you remember what I told you about elementary atoms? Everything under that would be an elementary atom. So the smallest possible atom number is 10,001. Then comes 0, 0, and 0, where, however, normally would be contained other numbers, namely the left subatom, the right subatom, and the atom value, where, remember again, a positive value would be an analogy atom and a negative value would be a vicinity atom. Remember again that the atom number is nothing else than the superatom. The left subatom is basically and the right subatom constitute the connection, and the value tells you what connection type it is. After having done that, we will be compiling the triangulation system itself. You have multiple variants for that. This is the uniprocessor version. Okay. Then there is also a multiprocessor version where I am using OpenMP. It is somewhat faster and somehow somewhat messier. I'm not exactly an expert in these things, so I did what I could, but, well, expect it to be messy. The uniprocessor version is the one which we are going to use because it is the most reliable, actually. And then there is one further version which I regard as super experimental, and it is the funniest and my favorite one. It is the OpenCL version. I have no clue of OpenCL. And the fact that with sleep deprivation and Red Bull and acorn syrup and cookies, I managed to still get that together in the last 2 weeks in the nights and going to sleep at 3 o'clock in the morning. Anyway, in the end, I got an OpenCL version as well. You can imagine how insane that version is and how unreliable. So we will be working with the uniprocessor one for now. Okay, So we are activating it. We're actually going to do that in a second. And then it will declare that the system is operational, and then you can say any symbol sequence. Here, I just said ABC, AAB. In my tests, that was not a bad sequence because it was giving a lot of triangles later on. You'll see that in a moment. I'm now going to proceed to display, to explain to you the display. This thing is actually going to show you how it is doing the evaluations, so to say how it is thinking, okay? And if you have no clue what it is doing, it looks just very fancy, but you have no idea what it does. So we're going to change that now. Okay, we just let it run, we gave it the sequence, we pressed enter, and it started to spit data at us. What is this data? First, you're having a line which is telling folding input array. It's going to present you at first several lines of zeros. This is basically one long array of up to n elements. In this picture it is 60, but I have later on reduced it to 36. Anyway, elements of the sliding input window, the thing I talked before when I told you about the context. And this input window is going to end with the atoms which we said. This is unfortunately not visible here because the yellow line is crossing it. But you said A, B, C, A, A, B. This was parsed into 16, 17, 16, okay? No, 16, 17, 18. So it will be 16, 17, 18, and then 16, 16, 17. Because it knows nothing, it can only do a hypothesis, okay? It is a hypothesis with a minimum vicinity value of 1000. If you don't know anything about an atom, but you have to assume that it is a good group of two input symbols, you're going to give it that value. The left subatom is 16, that is an A. The right subatom is 17, that is a B. The atom itself is 310,000. Okay, this is just the atom number. And yeah, that's basically your first atom. The sliding window basically will change during hierarchization. Do you notice, for instance, here, this grouping of A and B, which was at the end, is being done again in the beginning, right? So this is exactly how I was showing you in the very beginning of this slideshow, how A, B, C can be grouped together. Okay, this is exactly what's happening here. And this is going to continue until in this input array there's only one number left. That is the highest structure of the input. The whole thing, basically. And the system will continue to either seek knowledge or create hypotheses until it is done hierarchizing everything. Okay, let's look at some further details of the display. It is going to show you states of evaluation. It is going to show you here. Now let's go back once. No. Okay. It is going to show you here the triangulation. Okay. It is taking this atom here. This is the triangle side it is currently handling. And it is going to show you its conjugate and its cohabitant. In this case, it found a conjugate with this atom number with the left atom in common. And the right atom is different. Okay? So this is its conjugate atom, the second side of the triangle. This automatically gives you the cohabitant. I told you, if you know two sides of the triangle, you know the third. And it is telling you that this is a new triangle side. It is telling you here that it is concluded. It would normally write adjusted, like down here, if the triangle was known already. you see that the cohabitant is unknown also by the fact that it still has an atom number of 0. It did not yet get an actual atom number from recycling, that is, from killing the oldest atom and taking its atom number. You are seeing here a known cohabitant. It is having a valid atom number, it has one atom in common with the conjugate, and one atom in common with the original atom that is being considered. Okay, the original one is the 310,000. It has a left atom of 16. The cohabitant has 16 as a right atom. The conjugate has a left atom of 309,997, and the cohabitant has it also as left atom. Okay, this is just simply the third triangle side. And you're having here, basically for each one of them, the effect of triangulation on them. Okay, you're going to see how is this atom value going to change now that we did triangulation. Experimentally, that's quite interesting, most of the effects are positive. It nearly never happens that the triangle is actually negative. The system is quite effective at generating plausible structures and killing off implausible ones apparently very, very early on. So you're going to mostly see fitting effects, which are making things stronger. This vicinity value of -1000 is going to be increased. It is going to be increased by 2059. It is going to be -3059. This analogy value is going to be strengthened by 1732. It is going to become over 3000, and so forth. So this is the effects display. Further displays. Yeah, I told you, if a triangle is known, it is written that it has been adjusted. Now let's look at this line when it tells you, where it tells you state of evaluation. If you have a larger terminal window than me, you're going to see this actually on one line. This is really not two lines. You're going to see that this is the atom currently being considered. Its left atom is this, right atom is this, vicinity value is that. You're going to see which daydream it is. Do you remember this extension of the conversation? Okay, this hypothetical conversation. You're going to see which reconsideration it is, where it is basically trying to see again how the input should be structured. Each daydream has a number of reconsiderations under it. And it is going to show you a hierarchy value out of somewhere. Because here the sliding window has a size of 60, it can have up to 59 superatoms in it. Okay, so it is showing you how far it is. It will eject early once the entire input window has been reduced to only one number and zeros, like here. So this is why you're getting a reply down here. But normally it is really going to run through all of this. This is just because we're beginning and everything is full of zeros. But normally you will have to really wait until this is showing 59 out of 59, and then it is going to give you the reply. And in pos is the input position. That is, where in these zeros here did it actually perform its current grouping? Where did it pick something to group? No. Basically here, right? This is what was grouped down here. Okay, and here you are seeing the type of the connection. If in a logical triangle the side is positive, it is going to be written that it is ana, and if it is negative, it is going to be written that it is vic, that is vicinity and analogy. Vicinity and analogy have maximum values of plus 30,000 and minus 30,000. If any value is more positive than 30,000 or more negative than 30,000, it is being reduced to 30,000. We don't care whether it's higher. We need just simply, for technical reasons, prevent overflows. So once it has done everything, it is seeking a plan, and replying you with B. I am not showing here in this display the seeking of the plan. This I simply didn't regard as that important. But you are seeing what happens as a lead up to planning. And how to get out of the whole thing? Well, here you get the prompt to say something, and if you just press enter, it is going to write empty input interaction terminated, and you will be out of it. If you exit that way, the machine is actually going to learn what was discussed so far. Like all these atoms it generated are going now to become part of its knowledge base. And next time you run the program, it will be somewhat smarter, so to say. Okay, that was quite a lengthy introduction, but let us now have some fun with the actual thing, being this. Okay, I have compiled it already. I have generated already the elementary atoms, but let us do that just to be sure. Okay, the knowledge base has been now done. We're starting clean, okay? And we're going to give exactly the same input I was telling you about before. A, B, C, A, B. And that's what it looks like. Gives us the reply B, just as described before. Perhaps I should change the terminal size, because this is unfortunately not shown very clearly. Okay, yeah, this way is better. I'm now going to say A, B, A, B. Telling again B. Do you notice it is now doing more triangulations than before? And generally speaking, if I now scroll up a little bit, let's see whether I'll catch that. You see that now the input window was filling up more. It is not having so many zeros anymore. Let's tell it something really long. A, B, A, B, A, B. It is going to show you only up to 20 triangles. Like if it finds hundreds, it is still just going to show you 20. Yeah, so you see, folding the input array. In the end, it just got here. And then when it was trying to reply to that, finally it got to something which was that. I am now showing you examples with A, B, and C, and so on. But in reality, you can obviously use normal words. You can say, hello machine, it is fun with you machine. Talk to me machine. It's going to evaluate it just as well. C. That's a weird thing to say. I see. I see. But machine, I want to talk. Okay. Because we started with this A-B discussion, it is now kind of stuck with it. Machine, no more of this A-B thing. Just talk to me, machine. I want to talk to you, and I am curious about you, my dear machine. So talk. Okay. This is actually a little bit tiresome. Okay, you know what? We will now leave early. We will not let it learn that. Pressing Ctrl C leaves early, and now we will just talk with normal words. Hello machine, let us demonstrate it without teaching you nonsense in the beginning. So machine, talk to me machine. Okay, let's see what happens now. Okay, so just repeated me because it knows no better. But you see, it could in fact reproduce words as well. It is just really working with symbols. It doesn't care what these symbols mean. It derives meaning exclusively through form. And now, if we want to let it learn this conversation, we press enter. And that's it. Really, that's it. And I wish you much fun with this little gadget. I regard it as one of my masterpieces, which was most tiring to produce, and if you find bugs in it, please let me know. It was a nightmare to do the bug hunting. Thank you very much for watching. I wish you much fun with your own artificial intelligence experiments, for we shall progress with bravery and daring. And see you soon. Goodbye.